Okay, so let's take a look at this do now, just to kind of recap a little of what we were speaking yesterday in regarding to finding sums of arithmetic series. First of all, how do you identify when you have an arithmetic versus a geometric pattern? So remember that an arithmetic pattern means you're constantly adding by the same thing. Even though I know you see this fraction, if I maybe turn it in decimals, 3, 4.5, 6, etc., you're going to see that you're constantly adding by 1.5. Okay, so why do I need that? What I'm going to need to do in this problem, remember, if I want to find the sum of this particular series, I'm going to need to know how many terms I have, which we'll have to solve for in just a second. I need to know my first term, which is 3, and I need to know my last term, which is 78, and then I'm going to plug that into n over 2 times a1 plus an, which again is the arithmetic series formula. We're going to have a different formula when it comes to geometric series. So again, keep in mind that's specifically for arithmetic patterns. Okay, so for us to be able to figure out what our n value is and to also properly put this in sigma notation, I'm going to need to figure out what term did I, or what n value did I plug in to get that 78 as my last term. Well, let's go back again to making a rule for an arithmetic sequence. A sub n equals a1 plus n minus 1 times d. Well, my last term is 78, my first term is 3, n minus 1 is going to be left as n minus 1 because that's what I'm going to be solving for, and I know that my common difference, then the thing I'm adding over and over and over again, was that 1.5. Okay, so if I start going through and solving this, if I minus 3 from both sides, I get 75 is equal to n minus 1 times 1.5. Divide both sides by 1.5, and you'll find out that n minus 1 is equal to 50. So therefore, n is equal to 51. So I now can finish the calculation for when it comes to finding the sum. That would be 51 divided by 2 times 3 plus 78. And in this case, that comes to be a sum. To put this into sigma notation, okay, I set up my sigma. You want sigma to always go from n equals 1 to however many terms you have, and then you're going to put this arithmetic sequence formula right inside the sigma. So let's erase some of this additional stuff. So you're going to have 3 plus n minus 1 times 1.5 inside your rule. Okay, so you've now created this as a rule. Okay, so I really just went over that one because I wanted to go back over how you identify that it's an arithmetic pattern, what's the rule for finding the sum of an arithmetic series, and now I'm going to show you the rule for when it comes to adding up terms in a geometric series. The thing with this rule that you're going to have to be careful is just typing it in your calculator properly. I definitely recommend using that whole alpha y equals so you can get it set up to look like a fraction. Make sure you're plugging in the correct numbers. Even though I know it's a larger equation, what do you really need to have? You're going to need to know how many terms. You're going to need to know what's your first term. Unlike the previous problems we worked on, you don't have to know the last term, but you will have to know what your common ratio is. So remember that when it comes to geometric patterns, the difference is that you're constantly multiplying by the same thing over and over instead of adding by the same thing. So if you take a look at question number 1, find the sum of 4, 2, 1, 1/2, 1/4. Yes, of course you could type these 4 numbers in your calculator and add them together, but the idea is what happens if you have more than 5 terms? What if you have 100 terms and you want to add them together? Okay, this is what we call, by the way, a finite geometric series because there are a specific number of terms. We'll talk tomorrow about what happens when you're adding an infinite number of geometric terms. Okay, so first thing that I need is to list out the stuff that I said on the right-hand side that I will need to be able to plug into this formula. We need to know how many terms do we have. We have 5 terms here. 1, 2, 3, 4, 5. Okay, we need to know what's our first term. In this case, it's 4. We need to know what's the common ratio. What are we constantly multiplying by as we go from 4 to 2 and 2 to 1? Remember, if you can't see what the common ratio is, always just take a number and divide by the previous number. 2 over 4, or 1 over 2, or 1/2 over 1. Either way, you'll see the common ratio is 1/2. Okay, so my formula says, I'm adding up these 5 terms. It's my first term minus my first term times my common ratio raised to the nth power, not n minus 1 like we've done in our geometric sequence formula. This is just the nth power, divided by 1 minus the common ratio. So as I said before, I highly suggest that you take your time when you plug this in your calculator. If you don't have the ability to do alpha y equals where you could type, the whole numerator and the whole denominator separately, then make sure you use parentheses around that whole numerator and around that denominator, because that's the place where you're going to make a mistake if you do. Okay, when you actually plug that in, that comes out to be 7.75, and that is the value of that sum, which again, you could back up by actually adding 4 plus 2 plus 1 plus 1 half plus 1/4. Okay, so if you take a look at number 2, it says given the series and the number of terms, find the sum. So what do we need again? Or first of all, how do you know this is a geometric series? Well, as I go from 2 to 12, I'm multiplying by 6, and from 12 to 72, I'm multiplying by 6. The fact that we're constantly multiplying by 6 gives us a common ratio of 6, and that tells us it's geometric. That's how we know we're not going to do that pairs formula. We're going to use the formula that I have right up here in this box for a geometric series. So the formula is A1 minus A1r to the n all over 1 minus r. That's the sum of our terms. So we need to know how many terms we have. We have 6. We need to know what's the first term. The first term is 2. We need to know what's the common ratio. The common ratio is 6. So again, I'm going to take my time and plug carefully into my calculator. So my first term was 2 minus 2 times my ratio of 6 raised to the nth power, which is 6, all over 1 minus the common ratio. Okay, again, be very careful, use alpha y equals, and when you're finished, you'll find out the sum of these 6 terms comes out to be 18,662. Huge sum here, right? The reason why, if you remember, geometric series, or geometric sequences I should really say, are exponential functions. They grow exponentially fast, or they get small exponentially fast. So you'll notice with one of these ones that's growing, the terms get really big really fast, and that's why you'll notice you get very large sums in some of these situations. Okay, let's take a look at number 2. So again, the idea is that you're trying to find the sum, and you want to identify first, is this a geometric sequence? Well, as I go from 1 to -4, I'm multiplying by -4. And from 4 to 16, or -4 to 16, I'm multiplying by -4. So my common ratio is -4. You're going to have to be careful with that negative. My first term is 1. My common ratio is -4. How many terms do I have? 11. Thankfully, they give it to me. I don't have to actually find it. So my formula is A1 minus A1r to the n all over 1 minus r. So as I start plugging in, 1 minus 1 times -4 in parentheses raised to the 11th. Make sure you use those parentheses. All over 1 minus -4. Again, make sure you use parentheses. This is a common place where people make mistakes because they forget to put the negative twice, and you have to. Otherwise, you're going to get a totally different answer. Oops. So the sum of these, 11 terms, works out this case to be 838,861. As I said before, don't think you're doing something wrong because you got huge numbers. That's what happens with these geometric patterns. They grow really big, really fast. Okay. So if you take a look at question number 3, this is similar to question number 3 from yesterday's lesson. What you're going to be doing is finding, obviously, the sum of the terms of this sequence. So again, this is a great way of highlighting the difference between a sequence, just a pattern of numbers, and a series, what happens when I start adding the terms of that pattern together. Okay, so if you remember, what I need for a geometric series is I need to know what's the first term, 1 over 125. Okay, I need to know what's the common ratio. What am I multiplying by as I go from 1 over 125 to 1 over 25? Remember, if you get stuck, you can always take a term and divide by the previous term, and you'll see in this case you're multiplying by 5. The thing we're missing that we need is the nth, not the nth term, how many terms I'm working with here. So I'm going to have to, again, go back to my sequence formulas and use that to solve for n. For a geometric sequence, the rule was a sub n equals a1r to the n minus 1. The nth term we have here is 25. The first term is 1 over 125. The common ratio is 5, and that's being raised to the n minus 1 power. N minus 1 is what we're solving for. So you'll notice in this case, this ends up coming out to be an exponential function. So, okay, exponential equation. couple different ways you can approach this. I'm going to do it in a way that kind of like pulls back in stuff that we did in our previous unit just for review. If I start trying to get my exponential term isolated, I want 5 to the n minus 1 by itself before I start doing anything with logs or bases or anything like that. To be able to do that, I'm going to have to get rid of this 1 over 125 on the right-hand side. So if I were to multiply both sides by 125, okay, you'll notice on the right-hand side, 125 will cancel with 125, so I'll just have 5 to the n minus 1. On the left-hand side, comes out to be 3125. So if I think about powers of 5, the fifth power. Okay, you'll find out that the left-hand side comes out to be 5 to the fifth, and the right is 5 to the n minus 1. So once I get both sides to have the same base, that common base, I can drop my bases, I can set my powers equal, 5 is equal to n minus 1, and that tells me here that n equals 6. So I go back to my sum formula. Okay, I now have how many terms I'm working with. And so then I can sit there and say, okay, I'm doing a1 minus a1r to the n all over 1 minus r. So I have 1 over 125 minus 1 over 125 times 5 to the 6th power all over 1 minus 5. Okay, as you work that out, you'll see that that comes out to be a value of 3906 over 125 if you want it as an exact value, or if you want to approximate it, it's approximately 31.248. I do think that exact values are better than not having exact values, so I think you should probably leave it in that fractional form. And again, remember, you have a graphing calculator, which will do many of those things for you. Okay, so I want to scroll down to an example where they give it to you in sigma notation. And once again, just remind you of how you can use that information to plug into this geometric sum formula. So as you take a look at this, how would you know that this is actually a geometric series if you didn't want to sit there and plug all those values together? Well, the key is that it looks like an exponential function. It also sort of takes that look of a sub n equals a1r to the n minus 1, so you can kind of see here, oh, a1 might be something like 4. Obviously, again, that depends on if I'm actually plugging in 1 as my first term, so I would be careful with that. And most likely you can see that your common ratio, which is the base of the exponent, is -3, or in the second case, 2 and 1/3. So, again, you should recognize that it's an exponential expression, and that's what tells you it's a geometric series. Okay, so if I'm trying to do a geometric sum, remember that the rule is a1 minus a1r to the n all over 1 minus r. And when I say a1, I mean whatever term I get when I plug in the lower bound of that sigma. That might not always be 1. Okay, in this case, it is actually 1. So when I plug in 4 times -3 to the 1 minus 1, it turns out that 4 is actually my first term. That's what I got when I plugged in 1. Okay, I need my common ratio. As I mentioned before, your common ratio, that's like your growth factor if you think of it in terms of exponential functions, or what are you constantly multiplying by? You're constantly multiplying by -3. And again, you can identify that because it's the base of the exponential term. Okay, so in the next problem, we'll talk about a1 in just a second. Our common ratio would be 1/3 this time. Okay, I need to know how many terms I have. That is the same as what we had done in yesterday's lesson. Top number minus bottom number plus 1 tells me I'm dealing with 9 terms in this case. Okay, so the sum of these 9 terms comes from doing 4, my first term, minus 4 times my common ratio, which has to be -3, raised to the 9th power, all over 1 minus the common ratio, which again is -3. Be very careful with the way that you type that in. Again, you're going to get a pretty large number, so don't feel like you've done something wrong because you're getting something like 19,000. These exponential functions grow really big, really fast, so you should expect that they have pretty large sums. If you take a look at question number 6, the main thing I want to point out in this case, okay, 2 main things. A1, which is our first term, and again, if you could see me, I'm doing quotations with my hands around first term. The first term really comes from what are you getting when you plug in the bottom bound of sigma in for n. So my first term's not going to be A1 here. It's really actually going to end up being A5. That's your first term. Okay, so I'm doing 2 times 1/3 to the 5 minus 1. And when I work that out, again, use your graphing calculator, use math_frac, you'll see that comes out to be 2 over 81. My n value, again, comes from the top bound of sigma minus the bottom bound of sigma plus 1. Don't forget that plus 1. That's where most people make a mistake, and that tells you that you're adding 5 terms together. So I go back to my formula. A1, which in this case is a sub 5, really, the first term that you get when you plug into sigma. So 2 over 81 minus 2 over 81 times your common ratio of 1/3 raised to the nth power. And I'm going to put that all over 1 minus the common ratio of 1/3. Absolutely be careful with plugging this in your graphing calculator. Use parentheses, use fractions, whatever it comes out to be. This comes out to be an exact value of 242 over 6561. Approximately, if I was going to put that as a decimal, 0.037. So you can see this one actually comes out to be pretty small. That's actually something that we're going to address tomorrow. What happens when you have a growing exponential and a decreasing exponential, especially when we're not adding a finite number of terms, when we start adding up all of the terms in the series. Okay, and again, that's something that we'll address tomorrow. I still think that for your final answer, you should probably leave it as an exact value. And again, don't feel like you're doing something wrong if you're getting these fraction values or these very